Questions 21 through 25 on the 2007 Grade 8 Gauss Math Contest. In the diagram, ABCD is a square with the side length 6 and WXYZ is a rectangle with ZY equal to 10 and XY equal to 6. Also, AD and WX are perpendicular. If the shaded area is equal to half of the area of WXYZ, the length AP is. Let's blow this up a little bit. So, first and foremost, we need to label something. So, I'll label from here to here X. And from here to here we know is 6. So they tell us that that shaded region, which has an area of 6 times X, is equal to half the area of the full rectangle. And the full rectangle has an area of 10 times 6. Right? Length times width. So from this we can figure out X. So that means 6X is equal to 30, and therefore X is equal to 5. So X is equal to 5. Now, they tell us, if you remember, that this is a square, ABCD. So this is a square, and because it's a square, this side will also be equal to 6. So from B to C, that total region is 6. And very similarly, this total region is also 6. So if this region from here to here is 5, and therefore this is also 5, this is 1, correct? 6 minus 5, and that's what they want you to figure out, the length of AP. So the length of AP is 1, and therefore the answer to number 21 is A. Chuck the Llama is tied to the corner of a 2 meter by 3 meter shed on a 3 meter leash. How much area does Chuck have in which to play if he can go only around the outside of the shed? So let's draw this again here. So here we go. This is the shed approximately. And here I'm going to draw the leash like that. Was it 3? Yeah, 3 meters. So how can that leash move? Well, I'll show you. This is the leash, right? So he goes like that. That's his only way to move. And then when he gets to here, he can't go like that because he can't go inside the shed. So at this point, he can only go like this. So basically what that does is it forms the components of a circle. And I'll draw in those circles. So here we go. I've tried to draw the area the best I can. So he's basically going to be able to move all the way like that. And then once he gets to that point, he can only move this much. So we have to now figure out that total region. Well, it looks like it's 3/4 of a big circle. So 3/4 pi r squared plus 1/4 of a small circle. So 1/4 pi small r squared. This is the total area in which he can play. So 3/4 times pi, the big R is 3. And 1/4 times pi r, the small r, well, the leash is 3. This distance is 2. So that means this distance is 1. So that is what the small r represents, a distance of 1. So here we go. 9 times 3, 27 pi over 4. And this looks like just pi over 4. So it looks like 28 pi over 4. And that is 7 pi. So number 22, the answer is A. There are various ways to make $207 using only $2 coins and $5 bills. One such way is using one $2 coin and 41 $5 bills. Including this way, In how many different ways can $207 be made using only $2 coins and $5 bills? When I was a young boy, $2 was actually a bill. And then, I can't remember exactly, but sometime obviously later, it became a coin known as a toonie. Now, I don't know if people still refer to it as a toonie. I know they refer to a $1 coin as a loonie. But anyhow, that's just a little bit of a flashback for me. So what we want is some combination of $2 coins. So X represents the number of those, plus $5 bills. I'll let Y represent the number of $5 bills, and that has to equal 207. And the key is that we have to get integer solutions. X and Y have to be integers, and that's what this question boils down to. Well, they gave us one integer solution, that is X is equal to 1 and Y is equal to 41. If those are the numbers, this does indeed work out. You can verify it. It does indeed equal $207. So what we can do is we can just make a list and sort of see how this behaves. I'm going to start with, I think we can start with 0 for X, and let's just see what happens. There's several ways of doing this, but I'll just do it the simple way. If X is 0, Y will not be an integer. 207 divided by 5, like if you do this mathematically, you will get an equation that is Y is equal to 207 over 5, and that is not an integer. You can't have, 41 point something bills, right? The number of bills has to be an integer value. So that doesn't work. How about when X is 1? Well, we know that works for sure because they tell us that in the question. So similarly, we have to get integer solutions. Now, very quickly, you'll find out that this will only work when Y can be brought down to a certain very specific amount. And what I mean by that is that when you put in values for X and then you solve for Y, Y has to be an integer. And that can only happen if the remaining number is a multiple of 5. Okay? So for example, if X is 6, you have 2 times 6 plus 5Y is equal to 207. 5Y will be 207 minus 12, which is 195. And Y is therefore going to be 39. So that works. But did you notice this number is a multiple of 5? So we have to bring it down to a multiple of 5. And there's another way of thinking about it, which is if you get down to, say, another one, which is 11 and 37, you'll quickly notice that the Y's are just going down by 2's. So that's easier, in my opinion. And that's going to be the case all the way down to a Y value of 1, which would give X equal to 101. And if Y was 3, it would give X equal to 96. So this is basically, this scenario. And now we have to figure out how many of these there are. Well, it looks like it's every odd value from 1 to 41. How many of those? Well, 41 plus 1 divided by 2, which is 21. There's 21 of these sets. And that's pretty much all they're asking in this question. So number 23, the answer is E. A lattice point is a point xy in which x and y both are integers. For example, 2, 3 is a lattice point, but 4, 1/3 is not. In the diagram, how many lattice points lie on the perimeter of the triangle? There are several approaches to this question. I'll just do it in the way I like, which is simple way, is looking at it from the perspective of an equation of a line. So there's going to be 3, right? There's going to be the first line, which is from here to here. Then there's going to be another line from here to here. And then finally the third line. Okay? And then we can add up the lattice points. So the first one, which I can call this line right here, I'll just call that L1 like that. So that first one, L1, let's figure out the equation. And we have 2 points, so I can just plug those 2 points in. 1 and 2, so 2m plus b. And 12 and 21, so 21 is equal to 12m plus b. Subtracting, I get 10m is equal to 20, and therefore m is equal to 2. Substitute back into any of these, and you will get b is equal to minus 3. So the equation for L1 is 2m minus 3. Okay? So we have to make a little table and see what we get for lattice points. Well, we're starting here, so that's the first one, 2 and 1. And we're ending here, so that's the last one, 12 and 21. So we have to go up in terms of integer values. So 3, 4, 5, 6, like that. We're not allowed to use anything other than integers. But we have to figure out how many of these will give y values that are integers. Well, without going through the math, sorry, this should be an x here. Without going through the math for this equation, you will quickly realize that no matter what integer value you put in here for x, y will also be an integer. Okay? So that saves us a lot of time if you can recognize that. So that means all of these will give integer solutions. And how many of them are? There's 11 of those. All right? So in a very similar way, we'll do the same thing for the next line. And the next line will be here. Right there. Between those 2 points. And we can call that L2. So L2, in a very similar way, we'll figure out the equation. Y is equal to mx plus b. Plug in the first one, which will be 17 and 6. So we get 6 is equal to 17m plus b. And plug in that point, you get 21 and 12. So it looks like 21 is equal to 12m plus b. Subtracting, we get minus 15 is equal to 5m. And therefore m is equal to minus 3. Plugging m back into any one of those will solve for b. And if we do, we get b equal to 57. So our equation is basically y is equal to minus 3x plus 57. Okay? So in a very similar way, you make a little table and start with, we're starting with 12 this time, and we're ending at 17. And just like how I discussed in the previous line, if you put any integer value in that equation, y will be an integer. Okay? So that saves us time if you can immediately recognize that. So that means all of these will be integer values for y. So we have 1, 2, 3, 4, 5, 6. So 6 values that are integers. 6 pairs. 6 lattice points, basically. So now finally we turn our attention to the last one, which I will call L3. And in a very similar way, we'll figure that one out. L3, we can use the points 2, 1, and 17, 6 to figure out that equation. And as always, y is equal to mx plus b. And therefore, if we're using 2, 1, it becomes 1 is equal to 2m plus b. And if we're using 17, 6, it becomes 6 is equal to 17m plus b. Solving for this, if we subtract, we get 15m is equal to 5, and therefore m is equal to 1/3. Substituting m equals 1/3 back into any of those equations, and you'll get a b value of also 1/3. So our equation is y is equal to 1/3 x plus 1/3. Now for this, we do the same thing. We make a little table, And we're going from, let's see here, we're going from 2 to 17. Okay, so it's a little bit bigger this time. 2 to 17. But this equation will not hold true the fact that it will be an integer value for every value of x that's an integer, because these are fractions. For 2, when x is 2, we get 1. But for 3, it will be 4 over 3. And that is not an integer solution. That is not a lattice point. Very quickly, you will notice that y is basically x plus 1 over 3. So the only way this is going to be an integer is if x plus 1 is divisible by 3. And that happens when x is 5, when x is 8, 11, 14. Correct? So this gives me 1, 2, 3, 4, 5, 6. 6 lattice points. So let's see, how many did I get in total? I got 11, 6, and 6. 11 plus 6 is 23. But please take a little bit of time before circling 23 and moving on. Why? Because 23 is not the right answer. You say, well, why? What's the story here? You did everything correctly. I followed everything. Because we are facing a situation called overcounting, which is coming up on math exams more and more. And quite honestly, I myself have had my heart broken because of overcounting. And I take these things very seriously. I don't know how seriously you take them, but when I get a question wrong because I did something silly, it really pains me. And I want you not to make these types of mistakes. So, why did we overcount in this question? Because you can actually probably see it here. Look at that. I don't even have to really illustrate it. Do you see? Immediately, I counted 2 lattice points twice. Where? On each of the corners. That was counted twice, that was counted twice, and that was counted twice. Because, for example, this is going to be on this line, but it's also going to be on that line. See what I mean? That is going to be on this line and that line. And this point 17.6 is going to be on L2 and L3. So those 3 points were counted twice. So I have to subtract those 3 points from my total 23. And if I do, I get 20. And that is the correct answer. So number 24, the answer is C. A rectangular piece of paper ABCD is folded so that edge CD lies along edge AD, making a crease DP. It is unfolded and then folded again so that edge AB lies along edge AD, making a second crease AQ. The two creases meet at R, forming triangles PQR and ADR, as shown. If AB is 5 and AD is 8, the area of quadrilateral DRQC is, in centimeters cubed. DRQC, so we're interested in that right there. So I blew the diagram up a little bit. DRQC, this is what we are interested in. And the first thing I can do is just break this up into 2 sections like that. And if you do, half of it, or not maybe half of it, but at least part of it will be quite easy. This is AB, and that's 5. And they tell you that AD is 8. So immediately we can label those. Now, notice in this diagram, right here, up here, that CD was here. And then you folded it, and CD came up here. So when you do that, what you've basically done is formed a square. And because you formed a square, this is the same as that. in terms of its length, correct? So basically what that means is that since AB is 5, CD is 5, right, because this is a rectangle, and when you folded it up and CD kind of came up here, right, this was CD, if you look at it from that perspective, that CD is also going to be 5, correct? So that means that from here to here is 5. And since P is exactly across, like if you were to draw a line across like that, P is exactly across, that means from P to C is also 5. So if I were going to draw a distance, that's also 5. Okay? So that's the first thing you have to establish. And in a very similar way, for this crease that brings it to Q, it's exactly the same. From B to Q, it's also 5. Okay? Now that allows us to figure out the distance from B to P. If this whole distance is 8 and this distance is 5, then that means B to P is 3. And in a very similar way, you can figure out that Q to C is also 3. And therefore P to Q, that distance, is 2. Okay? So the very first thing in this red quadrilateral we can figure out is the area of this triangle right here. So that triangle, which is DCQ, is just 1/2 base times height, and the base is 5 and the height is 3, so that's 7.5. Okay, now we have to figure out this triangle right here. To figure out that triangle, what I'm going to do is first figure out the triangle PQD, which is this guy right here. PQD is right there. From that, I will subtract this one, PRQ. So PQD minus triangle PRQ, and whatever that is, I will then add to the 7.5, and therefore I'll got my answer. Okay, PQD is 1/2 base times height. The base is PQ, which is 2, and the height I can use this distance, D to C. So that's 5. Now we come to not necessarily the most difficult, but definitely a little bit of thinking involved here, PRQ. How do I figure out the area of PRQ? I have the base, that's 2, that's not a problem. But the height from there to there, how do I figure out the height? Well, I'll just draw in the height in red. First, let me remove that 2 there. Okay, so we're going to need to draw in the height. So here's the height right there. Okay? And let's blow this up a little bit. Now, how do I figure out that height, that red line? Well, this is where angles come in. This angle right here is going to be needed. How do I figure that out? Well, remember, this essentially, when it was folded, formed a square. So that crease is the diagonal of a square. So if you were to look at that angle is 45 degrees. And because it's 45 degrees and this is a right angle, this is also 45 degrees. So this is an isosceles triangle where this side is the same as that side. And this whole side was 2, so therefore half of it from here to here is 1. And therefore this is also equal to 1, since it is the other side of the isosceles triangle. So there you go, you just got your height. Height is 1. So I can now figure out the area of PRQ. PRQ is 1/2 base times height. The base is 2 and the height is 1. And that looks like it equals 5 minus 1, which is 4. So now to figure out the quadrilateral DRQ, I just have to add this, and if I do, I get 11.5. And therefore, the answer to number 25 is D.